So let's get started again. And as a continuation of what we just discussed, this is a simple brain teaser, if you will, to see how you can apply um, some of what we have just talked about here in the context of events. Okay, so I shall provide you a guideline as to solving these kind of problems, and hopefully it'll sound easier than what it feels like when you first look at it. Okay, so a retired Ohio State trooper has determined that in routine traffic stops, there is a 10% chance of the driver having a firearm in the car and having an expired driver's license. Further, 60% of these stop drivers have valid driver's licenses, while 60% either have a firearm or an expired driver's license. So the question is, what is the probability that a stop driver has no firearms in the car? Okay, so the first step of the puzzle, because there's too many numbers out there, percent, 10%, 60 here, there, and it has a natural tendency to confuse you. Okay, so the easiest option here is to first ask yourself, what are my broad categorical variables here? Okay, one is a firearm, the other is a driver's license. So within a firearm, there are two subsets. Either you have a firearm or you don't. Within the expired license set, there are also two options. Either your license is valid, which basically means you don't have an expired license, or you have an expired license. So that helps you generate then your two-way table. And then you start plugging and playing with it. So even before you put anything else, once you start putting in these probabilities, of course, the numbers will start making sense. The first thing you should start off with is definitely the overall outcome probability, because that thing is not changing, it's not going anywhere. Okay, so that one is your eventual final, the absolute finality. Okay, the total state space within which all of this is happening. Now, the first line says that there is a 10% chance of the driver having a firearm in the car and having an expired driver's license. So yes, a firearm in the car, yes, an expired driver's license, that probability is 10%. That's how you fill that up. Then it says further 60% of these top drivers have valid driver's licenses. Okay, so in other words, 60% of the drivers who are stopped do not have an expired license, have valid driver's licenses. Doesn't matter. This sentence talks nothing about whether they own a firearm or not. Okay, so then that becomes a marginal value for you. So that's where that data is ready. That data is ready. It also tells you that 60% either have a firearm or an expired driver's license. So we'll look into what that means in the context of either or, right? So if you remember, probability of A or B, and this is happening only when you have a scenario where you have A, you have B, and there is some common grounds between them. So we said that probability of A or B is probability of A plus probability of B. Well, wait a second, I have taken the common ground twice, and therefore I subtract the common section of them. So that's the way of capturing the probability of two events, A or B. So we'll get to that 60% of firearm or expired driver's license in just a second. Now that we have captured your 10, we have captured the 60 here, let's look at what all we can fill in before we look at that final aspect of probability of A or B, right? So knowing that the marginal value here is 0.6, can I capture or compute the marginal value here, knowing nothing else? Yes, no? Yes, right? Because at the end of the day, these marginal values should add up to what?
1.
1 or 100%. So this marginal value is 0.4. Everybody agrees. Okay, just by virtue of the way it is set up. And because this value is 0.4, what can he say about this value here? So if you have an expired license, yes, the total probability is 40%, of which 10% comes from yes firearms, So the remaining 30% will have to come from no firearms. So they basically add up to that marginal value. How do you get this marginal value? By adding up these two values, right? So this is 0.30 and that's 0.40. We have still not looked at this statement, and we will eventually look at that. Anything else that we can compute from what is given to us other than that statement? Oh, by the way, what is it that I'm after? What is the probability that a stopped driver has no firearms in the car? A stopped driver. So everybody here is a probability for a stopped driver. No firearms in the car. So no firearms in the car, which basically means I'm looking at a marginal value here, right? And I'm trying to find what this value here is. That's what I'm after. Still with me? Okay. So now let's look back into that question. 60% either have a firearm or an expired driver's license. So probability of a firearm yes or expired license yes. Okay. That's basically what I'm talking about. That probability is 0.6, right? That's what is given to me. You guys still with me? Yes, no? So probability of a firearm, which is yes, it could be firearm no. So I'm choosing the specific event. Probability that I have yes, I have a firearm, or probability that I have an expired driver's license. That probability is 0.6, right? 60% either have a firearm or an expired driver's license. So when you apply this formula or the rule of probability, if you break that up, this basically becomes probability of a firearm yes plus probability of a expired license yes minus probability of a firearm yes and an expired license yes equals 0.6. So now let's look into which one of these we know, which one of these we don't. So probability of a firearm yes, which basically is this one, right? The overall marginal value, you don't know that value. Probability of an expired license yes. What's that probability? We have already computed that. What's the probability that a stop driver has an expired license?
0.4.
Somebody. Ashley?
0.4.
0.4. So that is basically the probability that somebody has an expired license. So what's the probability that somebody has a firearm and an expired license? What about this guy here? Is it given in the problem that somebody has a firearm and an expired license? That's this 10, right?
Right.
So now you are suddenly seeing that in this equation, the only unknown is this guy. So if I rewrite this, it's the probability of a firearm in the car plus probability of an expired license, which is 0.4 minus probability of a firearm and an expired license, which is 0.1, which is equal to 0.6, right? That's basically my overall function here, the OR. And so now what is the probability of having a firearm?
.3.
So if you take the plus 0.4 and minus 0.1 and you take it to the other side of the equation, that becomes plus 0.3, and so 0.6 minus 0.3 becomes 0.3. So probability that a stopped driver is having a firearm is 30%. Where would that go here in this cube, in this box? Is it a marginal or a joint probability? Nick?
Marginal.
Marginal, right? The probability that somebody has a firearm. So that goes all the way here. This is your 0.3, right? Now can I compute this guy?
Yes.
Right, then it is 0.7. And I can actually compute the rest of everything else. So this guy then becomes 0.2 because 0.2 and 0.1 makes it 0.3. And this guy becomes 0.4, and 4 plus 3 is 7. Everything adds up. So I can go 9 different yards with the problem depending on what has been asked of me. Again, step 1 is always find variables. Okay, once you find your variables, step 2 is draw. Step 3, insert given values, and we basically build from there. So from a probability standpoint, we have looked into it from different angles. We have looked into the probability rules, and we talked about those rules as early as our two-way tables when we started talking about joint probability, conditional probability, marginal probability from last week. We brought them back here more from a rules perspective. We looked into counting, we looked into combinatorics, we looked into ways to count, we looked into the difference between what permutation is, what combinations are, when to use permutations, when to use combinations. And eventually we put a probabilistic spin to it and said, well, at the end of the day, only when you are able to count the occurrence of a certain event can you actually find the likelihood of that event happening. Because the likelihood is nothing different from the idea of a relative frequency. So the occurrence of a specific event relative to all possible occurrences. That is what the probability is. And that's why, if you recall our discussions on permutations and combinations and the examples that we worked off with them, we looked into the count first. And then based off of that count, we found a total count, a count for a specific event, and just took that ratio. And that then became the probability of what we want to find. So two things I want to discuss for the rest of this class. The first one is more of an observation than anything else. Let me see if I can find it. Okay, so can everybody see my Blackboard site on your screen? Yes, no? Can you see my Blackboard site? Yes?
Yep.
Yeah.
Okay, so if you look under data sets used in class, what I have put in there is for week 6, I have put in a few things to study. One is I have put in 3 videos of Z applications, and these should be an interesting read as you have now completed the learning module 3 of using Z. And in fact, the 3.5 video alluded to a certain specific application of Z in the context of vendor management. And so these are neat applications in terms of quality management, where the Z concept is very easily applied, which is what that first video is here. And then there is a very neat application of a concept called TrueCar that is widely used in the car industry today. And you'll also see that it's a standard application of the Z concept. And then of course, our old friend suntan lotion with advertising dollars and temperature is revisited. And this time we are looking into how we can continue with that understanding of the data set by using the concepts of Z and probability. So make sure that you review all of those 3 videos, and that'll give you a more grounded understanding of Z. Now, in that 3rd video, the suntan lotion video, there is an Excel file used, and I have provided that Excel file as an attachment here. It's called zsuntanlotion.xlsx. Okay, so when you are reviewing that 3rd video, make sure you can open that Excel file and work along with my video. That way you'll understand what is going on there. And last but not the least, I have another PDF file called Probability and Counting Practice. I want you guys to open that file right now. Okay, so one more time, from your course content data sets used in the class, under week 6, you'll find an attachment called Probability and Counting Practice. And let's work on this together as a class, because hopefully that will then reinforce some of the learning that we have had so far. Okay, so okay, good. So simple example, the number of vehicles in one randomly selected parking lot at Indiana State University was cross-classified by parking sticker and type of vehicle. So in essence, these are your 2 categorical variables, right? Parking sticker and type of vehicle. And so your vehicle type is either an SUV, a minivan, a sedan, or something else. And then your parking sticker is either it's a student or a faculty staff, or nothing is displayed. Okay, and so these are the counts. Okay, so the number of vehicles. So it's not the probability that has been captured here, it's the count that has been captured here. And of course, the total count is 140. Okay. So now, if one of those vehicles is randomly picked from the parking lot, what is the probability that it's displaying a student parking sticker? And I just need an expression.
Would it be 41 divided by 140?
Very nice, Ashley. So Ashley says that the probability that the specific random vehicle that I have picked from the parking lot will display a student parking sticker, which basically means this is your student parking sticker, irrespective of whatever car it is, that's your marginal total value, right? And so your probability would be 41 divided by 140. Everybody with me on that? If you have questions, this is your time to ask. Don't hesitate. Don't think what others would feel if you have a question. Others are not paying for your class. And as far as I'm concerned, I'm the dumbest guy in this class. So, bring it on. If you are stuck, let me know. But you want to get this right. Questions? So on that same note, what's the probability that a randomly picked vehicle would be a sedan?
50 out of 140.
50 out of 140, because you're looking into just a sedan. Doesn't matter what kind of parking sticker is going with it. It's just a sedan. So there are 50 sedans. So 50 out of 140. A sedan displaying a student sticker. So let me hear from somebody else, somebody who has not. I've heard from Ashley and Nick already. The Davises have spoken. How about that? A sedan displaying a student sticker?
Is it a 24 by 50?
It's 24. Well, hold on a second. You are still looking at a vehicle that's randomly picked from this parking lot. So one out of a certain vehicle picked out of 140 possible vehicles, right? So what is the
It would be
probability of a sedan displaying a student sticker? 24 is correct.
24 divided by 140.
24 divided by 140. It's the total count from which you are looking at. Because Timothy mentioned 24 out of 50, I'll pour the poison back into his veil, okay? So Timothy, if I have to give an answer of 24 out of 50, how would you represent that? How would you explain that?
So the probability, are you asking about the probability?
Yes, so 24 out of 140 represents the probability of choosing a vehicle randomly from the parking lot, which will be a sedan displaying a student sticker. Okay? 24 out of 50 tells us something. What would that be? And I'm distributing this poison. It's open to anybody else in the class, not just for Tim.
Dr. B,
Yes.
would it be the conditional probability of a student having, of a sedan being having a student parking permit?
So in other words, it's choosing a vehicle with a student parking sticker, given that the vehicle is a sedan. So that then becomes the condition within which you are looking at that 24. So Tim, that is what you were alluding to, but that's a different concept. You see what I'm saying?
Yes.
Probability of a minivan or a car that's displaying a faculty staff sticker. So what's the probability of a minivan? Let's break it up. What's the probability of a car being a minivan?
42.
42 out of
140.
140. That's the probability of a car being a minivan. So this is the minivan piece. 42 out of 140. What's the probability of a car with a faculty staff sticker? Somebody else? What's the probability of randomly picking a car with a faculty staff sticker?
89 out of 140.
Thanks, Lauren. 89 out of 140. So my question is, probability of finding a minivan or a car displaying a faculty staff sticker. So what else do we do?
Class.
Probability of A or B is probability of A plus probability of B minus if there is anything common between them, right? So probability of a minivan or probability of a car displaying a faculty staff sticker would, as Ping said, it will be a plus. That's the probability of event A plus the probability of event B. But then, is there a situation where there is a common ground of a minivan and a faculty staff sticker? That's 35, right? So that has been considered twice in the consideration of an OR, which is why it has to be subtracted. So that then becomes minus 35 over 140, right? Because if you really think about this as only two events, then if you're capturing the probability of both those events, the common shaded area is been captured twice. And so one of them have to go. And that one of them is in essence, okay. One of them is in essence, this guy here, right? So that is the commonality between minivan having a faculty staff sticker. Okay, so that has been captured twice. If I just add up this guy, that includes 35. I add up this guy, that also includes 35. So one of them has to go to keep it unique. So therefore 135 gets out of the total addition. And that's where the concept of the OR comes in. If they were completely mutually exclusive, then that final term doesn't matter. They're already mutually exclusive. So it's just an addition that we have learned from our previous class. Anytime we say OR, what do we say? We add, right? That's for mutually exclusive events, there is no overlap. So that final term doesn't have to be there. The final term is basically taking care of that overlap because you're considering it twice in your count. So to take one of them out. Still with me? Yes, no? Last, an SUV given that it is displaying no parking sticker. Given that it is displaying no parking sticker, so the probability of an SUV given that no parking sticker. Okay, so then that becomes the probability of the SUV and no parking sticker divided by the probability of the cars with no parking sticker, which if you go into the numbers, SUV and no parking sticker is 3 and no parking sticker across the board is 10. So it will be 3 over 140 over 10 over 140, which is 3 over 10 or 30%. These are the logical aspects of analytics. It doesn't need you to compute any hi-fi software to get to these numbers. This is just logical aspect. This is where the idea of a state space comes in. There are only a certain set of events happening. How do you look at that mix of those events? What happens, what doesn't happen? How do you go about looking at those possible mixes? And that's the name of the game here. Okay. Any questions so far? Questions? Easy enough? Last piece. Assume that 4 vehicles are to be selected randomly from this parking lot without replacement. What's the probability that all the selected vehicles are sedans? So let's go back to the discussion that we started this class with. We are trying to find the probability that 4 vehicles are to be selected randomly from this parking lot. And specifically, I'm looking at an event where all those 4 vehicles are sedans. So my first question to you is, how many vehicles are there in the parking lot? Come on, guys. How many vehicles are there in the parking lot?
140.
140. Does everybody get that? So if I have to choose 4 vehicles randomly from a list of 140 vehicles, in how many ways can I choose 4 vehicles? Just give me the expression.
$140C4.
Thank you. So 140 C4 is the total number of possible ways in which you can choose 4 vehicles. Recall, the probability is nothing but a relative frequency. So you're trying to find the specific scenario, and this is your numerator that I'm trying to find, in which I'm choosing 4 vehicles such that all of them are sedans. So what would the numerator be? How many sedans are there?
50.
So of those 50 sedans, how many will be chosen?
Or
All 4 will be chosen, right? And you could go ahead and say, of the remaining, how many remaining vehicles are there? If 50 are sedans.
90.
90 remaining vehicles, total is 140, right? So of those 90 vehicles, how many will be chosen?
0.
0. And that basically is 1. So you don't even have to include that term. It's just 50 C4 over 140 C4. And that ratio is the probability that all the selected vehicles will be sedans.
Dr. B,
Yes, ma'am.
does it matter that the vehicles are selected without replacement?
The without replacement basically ensures that they're all unique.
Okay.
That is where it ensures that they're unique. Now, the last part of my day, I promise I won't torment you anymore. What's the probability that at least 2 of the 4 selected vehicles are sedans? So first, let's talk about the denominator. Does anything change in my denominator from the previous problem? I'm still trying to choose 4 vehicles from the parking lot. What's the probability that at least 2 of the 4 selected vehicles are sedans? So the number of ways I can choose 4 vehicles from 140, does that change?
No.
So overall number of ways I can choose 4 vehicles still remains the same, right? However, in the numerator, I'm trying to find the probability that at least 2 of the 4 selected vehicles are sedans. So at least 2 means what?
2, 3, 4.
2 or more. So I can have a set of choice in which I have 2 sedans, or I can have 3 sedans, or I can have all 4 as sedans, right? Yes, no?
Yes.
So in the previous example, we just talked about the fact where all 4 are my sedans. So that value is 50 C4, right? So of my 50 sedans, all 4 of them are chosen. What is a scenario when I choose 4 vehicles of which 2 are sedans? How do I write that? So of my 50 sedans, how many are chosen?
2.
2. And of the remaining 90 vehicles, how many are chosen?
2.
Say it loud.
2.
2. So that's one option, right?
Yeah.
What happens when it comes to 3 sedans? Of my 50 vehicles, how many are chosen?
3.
And of the remaining 90 vehicles, how many are chosen?
1.
1. So what does the or sign do here? it basically adds these things up, right? So it essentially goes 50C2 times 90C2 plus 50C3 plus 90C1 plus 50C4. That then becomes your total number of possible ways in which you can choose the 4 vehicles such that at least 2 of those 4 are sedans, 2 or 3 or 4. Your denominator remains still the same. And it's this ratio that then becomes the probability of choosing at least 4 vehicles, or at least 2 of the 4 vehicles which are sedans. Make sense? Yes, no? I see a thumbs up from
Yes.
Sarah Shikora. About the others? So let's put this all together in the context of a distribution, if you will, and hopefully that should be the parting thought for the day for today. You can all see my slides, right? Can you see my slides again?
Yes.
So here is the idea about constructing a probability distribution. Okay, so if you really think about tossing a fair coin twice, okay, and here is the idea of a fair coin. What does a fair coin mean?
It's an even 50-50 split, heads or tails.
It's an even 50-50 chance of a heads or tails. I have seen multiple movies in which that is not necessity, but other than that, mostly coins are fair unless there is a certain distribution of the metal on one side, and every time you flip it, it falls on that end. That's how gambling is done. So if you look at a fair coin, if you toss a fair coin twice and construct the probability distribution of the occurrence of a head, the idea is how many possible outcomes can there be? Okay, so I have taken a coin, I have tossed it twice. It is very much possible that I don't find a head either of those tosses, right? So it can be 0 heads, it can be 1 head, it can be both heads. Okay, so the idea of an outcome therefore is the probability that head becomes 0 is a tail from the first toss and a tail from the second toss. And each one of them are 50%, which is, when you multiply those because of the and, in total there is a 25% chance that both times you toss the coin, you'll not find the head, given that it's a fair coin. What's the probability of 1 head? And this is where the fun begins, because they are both unique outcomes. The first time you toss, it becomes a head. The next time it becomes a tail. That's one event. The first time you toss, it becomes a tail. The second time it becomes a head. That's also another event. These two are distinct events in which the first case, the head happens on the first toss. In the second case, the head happens in the second toss. And so both of these could happen and could qualify for the possibility of a 1 head. So it's a head and tail, or a tail and head, which is where the idea of a 0.5 times 0.5 plus the 0.5 times 0.5 comes. So that's basically what your 50% is. And then of course, the remainder of this, you don't even have to calculate this. All of this totality is 100%. This is 50, this is 25. Together it's 75. So the remainder is 25. It's a given, but that's where that remainder comes from. So both times you toss it, it becomes a head and a head. And so these kind of distributions can be drawn or constructed for any kind of trial where it doesn't have to be a 50-50. It can be a 30-70, a 40-60 mix. And you can actually draw these distributions for all of those possible trials.